Alright guys, so in this video we are going to introduce the polar plane or the polar coordinate system. And we're going to say that the polar coordinate system is an alternate way for us to define a point's position on the plane. Now the way that we're most used to defining a point's position is with the Cartesian coordinate system or the xy axis. And here we define a point's position by its vertical and horizontal displacement from the origin, right, which is where the x-axis and y-axis meet. So right here, if we've got some point on our plane, let's say this point right here, we would say that this point has some horizontal displacement, we'll call A, which we measure on the x-axis, and some vertical displacement we'll call B, which we measure on the y-axis. And of course, the x value and y value come together to give us the ordered pair AB, which give us the position of our point with respect to the origin. Sometimes xy coordinates are called rectangular coordinates, and that's because the horizontal and vertical displacement can make a rectangle with the origin, right? So in the textbook you'll hear about an ordered pair xy defined as rectangular coordinates. Now with the polar plane, what we're doing is we are defining a point's position with a rotation from standard position in the direction of the point, and then a direct distance to the point, right? So looking at this point right here, we would say that the polar coordinates that define the point would first be a rotation in the direction of the point, and then a direct distance to the point. We call, of course, that rotation some angle theta, and we're saying that the direct distance is going to be a length which we define as r. And the polar coordinates are going to be r theta. So right here what we're going to do is get used to our polar plane. We're going to go through and plot some points and talk about some vocabulary. And then in our lesson on Wednesday, we're going to talk a little bit more about graphing functions on the polar plane. So right here, we say that the pole we define as the origin, and that is basically the ordered pair 0, 0 on the xy axis. We say that the polar axis is the positive x-axis, and we define that as the polar axis because, of course, that's where all our rotations are going to start from when we rotate from standard position. Ordered pairs are defined as r theta, where r is the direct distance and theta is the directed angle. In general, right here, we've got a point 3 2/3 pi, where we've got 2/3 pi as the direction that the point is located in as a rotation from standard position, and 3 is the direct distance to the point from that rotation. So right here we've got a polar plane represented where we've got sort of rings that go out from the origin in increments of 1 unit. So we have all the rotations on the unit circle except for the half quadrant rotations. So that would be the rotations that would be either increments of pi over 4 or 45 degrees. So right here, this is a 6th pi, that is a 3rd pi, and if we're looking at our rotation theta as 2/3 pi, that would be the rotation that takes us to our first stop in the second quadrant, right? So that's the direction our point is located in. Now right here we would say that the r value is going to be the distance from the origin in that direction. So basically right here we would say we would go out a length of 3 in the direction of 2/3 pi to our point. So I'm going to count out units with these rings. We would go 1, 2, and that right there is the point 3 2/3 pi on the polar plane. Now, one thing I want to talk about really quickly right here is the polar plane and the Cartesian coordinate system of the xy axis are just two different ways of talking about a point's position. Really, we're talking about a point on the plane, right? And the origin is just our perspective of where we start defining that point. So in general, it's not like this point right here that we're seeing is a different point than it would be on the xy axis. We're just defining this point with a different way to give us its position, right? From the origin, which is of course either 0, 0 on the xy axis or the pole on the polar plane. Okay, so let's take a look at 2 more points here. The next point we want to look at is the point 1, negative pi over 6. And so right here, what we're basically saying is that negative pi over 6 is going to be a rotation down into the fourth quadrant, and then we're saying that our point is going to be a length 1 unit away in that direction of pi over 6. So if we're plotting this point, we would say we rotate down to that first stop in the fourth quadrant, and then we would go out a length of 1 in that direction. Now right here, I'm drawing the angle that we're seeing right here, but in general, you wouldn't really draw that angle in. You would have your polar plane represented in this way where you could sort of see the angles more clearly, and you would just sort of plot the point the way you would on the XY axis when you get more comfortable with the polar plane of the polar coordinate system. Okay, so with our next point, we've got something more interesting. Here we have a negative r value, right? Our theta is in degrees. So right here, what we're saying is, what we're going to do first is rotate to 225 degrees, which is a rotation that is a half quadrant rotation into the third quadrant. So right here, we rotate all the way around to 225 degrees. And then right here, with a negative r value, we're saying that instead of going forward into the third quadrant, because our r value is negative, we're actually going to go backwards into the first quadrant. So a negative r value actually means that we're going to be going in the opposite direction that our angle is telling us. So right here, we're going to go 3 units backwards to 3. And right here, this is the point, negative 3, 225 degrees. So right here on our next page, we've got some points for you to plot, and then we're going to answer some questions about points on the polar plane. So why don't you guys go ahead and pause the video here, and we'll come back and look at this work in a second. All right, guys, so right here with our first point for 3/2 pi, we rotate to 3/2 pi, and then we go a distance of 4 down the y-axis, so 1, 2, 3, 4, and that gives us our point right there for 3/2 pi. With our second point, we have a rotation that is 150 degrees, and then we have an r value of negative 2. So we'll rotate that 150 degrees, which is all but 30 degrees of a half rotation. And then right here, we're going to go in the opposite direction, which will take us 2 units backwards into the fourth quadrant. Right here with our last ordered pair, we've got 3 and then 8/3 pi. So 8/3 pi is actually more than a full rotation. 8/3 pi is actually 2 and 2/3 pi. So right here we go all the way around, and then we go an additional 2/3 pi past the full rotation, which takes us to the first stop in the second quadrant. And then, of course, we're looking to go a length of 3 units in that direction. So we would count out 1, 2, and then 3. And that is the point 3 8/3 pi. All right, guys, so now what we want to do is ask ourselves some questions about our polar coordinates. And the first question we're going to ask ourselves is, will each pair of polar coordinates define a unique point? Really what we're saying here is there a way for us to interpret our polar coordinates so that we wouldn't get just one point or a unique point? And if we think about it, when we're rotating in some direction, right, and then going a distance r in that direction, either forwards or backwards, really we're always going to end up at the same point, a unique point. And so in general right here, what we can say is that each pair of polar coordinates will define one unique point. There's only one way for us to interpret our polar coordinates to get to a position on the polar plane. Our next question is, will each point be defined by a unique pair of polar coordinates? And this is a more interesting question. Right here what we're asking is, are there some other pairs of polar coordinates that will take us to the given points that were defined here? And if we look at our last example, in our example C right here, what we're seeing is the same point that we plotted on the first page with the ordered pair 3 2/3 pi. So what we're seeing here is if we have the same r value, then any coterminal angle will basically take us to the same point, right? We can also think about what would happen if we had the negative of an r value. So right here, if we've got negative 2, if we take a look at what would happen if we had an r value of 2 and let's say a rotation of 330 degrees, what we can see here is that rotation of 330 degrees is going to be a rotation that is all but 30 degrees of a full rotation, and then that direction of positive 2 is going to take us 2 units forward to the same point, right? So really what we're looking at is 2 different ways in which our polar coordinates could be defining the exact same point. And in general, what we can say is if we want to come up with all of the polar coordinates that will define a point, we'll say the generic point r theta, we can say that if we have the same r value, any coterminal angle to theta, which could be defined as theta plus 2k pi, where k is an element of the integers, will take us to the same point. So these 2 guys are defining the same point on the polar plane. Similarly, we can say that if we have a negative r value, a rotation that takes us in the opposite direction, so we could say theta plus pi, will also take us to the same point as r theta. Now right here, we also have to take into consideration all coterminal angles of this angle right here, theta plus pi. So we would have to say 2 plus 2k pi here as well. In general, right here, if we factor pi out of these last 2 terms, what we're going to end up with then is a negative r, and then theta plus, right here we would have 2k plus 1 pi, which is basically an odd increment of pi, which is a rotation that will take us in the opposite direction from our theta. So right here, these 2 sets of polar coordinates define the same point as r theta. All right, guys, so right here what we're looking at is converting polar coordinates to rectangular coordinates and rectangular coordinates back to polar coordinates. In our first example right here, we want to convert the polar coordinates defining our point 3, 120 degrees to rectangular coordinates for an x, y ordered pair. So right here, the way we're going to do this is we are going to extend a vector from the origin to our point, right? And when we extend a vector from the origin to our point, we can see that the magnitude of the vector, or the distance from the origin to the point, is actually given to us by that value r, 3. And right here we can say that the direction the vector goes in is actually the direction we have to extend from the origin to get to that point, which is 120 degrees. So actually right here, our polar coordinates are actually giving us magnitude and direction for our vector. Now, since we're extending from the origin, we can say that in component form, we actually have the horizontal component as the x value of the ordered pair and the vertical component as the y value of the ordered pair. So right here, if we can get our vector with magnitude 3 and direction 120 degrees in component form, then we essentially have the ordered pair xy. So right here, we can say that with magnitude and direction, we can define component form for our vector as 3 times cosine of 120 degrees for our horizontal component, and 3 times sine of 120 degrees for our vertical component. And that essentially gives us approximately negative 1.5 when we evaluate 3 cosine of 120 degrees as our x value, and right here 2.6 when we evaluate 3 sine of 120 degrees for our y value. Now the reason I'm saying approximately is because actually this 2.6 isn't an exact value. I rounded to get that, but this is basically where we're seeing that point on the plane in terms of an xy value ordered pair. Okay, so let's talk about converting rectangular coordinates to polar coordinates. Right here, what we're going to do is basically the same thing. We're going to convert rectangular coordinates to polar coordinates using vectors. So right here, again, I'm going to extend a vector from the origin to our point. And when I do that, the xy value at the head of the vector is the component form. So right here, I can say component form for my vector is going to be 3 for the horizontal component and 2 for the vertical component, right? Now right here, if I have component form for my vector and I'm looking to get the r value of my polar coordinates, which is of course the magnitude of the vector, and my directed angle theta, which is of course the direction of the vector, then right here I can go through and use the things that I know about vectors. So right here we're going to say that that theta is going to be inverse tan of the vertical component of 2 divided by the horizontal component of 3, which is approximately 33.7 degrees. And then right here, if we're looking for the r value, we know that's going to be the magnitude of the vector, which is, of course, the distance from the origin to the point at the head of our vector. So right here, we can say that with r, we really have the magnitude of our 3, 2 vector, which is going to be the square root of 3 squared plus 2 squared, so that's the square root of 13. And so right here we can say then that the polar coordinates for our ordered pair 3, 2 are going to be square root of 13, comma, 33.7 degrees. All right, guys, so we're going to let you try a couple of these on your own, converting from polar coordinates to rectangular coordinates and from rectangular coordinates to polar coordinates. We're going to use vectors extending from the origin to our point to do this, and we'll take a look at this in a second. All right, guys, so for this first one, when we want to convert these polar coordinates to rectangular coordinates, or an xy ordered pair, we want to extend that vector from the origin to our point. We know that then the r value would be the magnitude of the vector extending to that point, and the directed angle would be the direction of our vector. So right here we can get component form by saying 4 cosine 240 degrees will be our horizontal component, and 4 sine of 240 degrees will be our vertical component. And of course, since we're extending from the origin, we know that the horizontal and vertical components of our vector will be the x and y value for the point at the head of our vector. And so right here what we can say is that we have -2, -3.46 as the x and y value of our vector when we evaluate 4 cosine of 240 and 4 sine of 240. All right, guys, so looking at the next one, we are converting from rectangular coordinates to polar coordinates. Right here, we have our point in the second quadrant, so we extend our vector from the origin to that point. Now, when we're evaluating the direction of our vector, we want to do inverse tan of the vertical component divided by the horizontal component, but because we're extending into the second quadrant, we're also going to add 180 degrees, and that gives us the angle of 116.56 degrees as our directed angle, or the direction that our point is in. And then, of course, the r value is going to be the magnitude of our vector, which is, of course, the distance from the origin to our point. So right here, when we get the magnitude, we get square root of 20, and that gives us our polar point as an r value of square root of 20 and a theta of 116.56 degrees. All right, guys, so we'll look at more of this stuff in class. All right.